11th problem, we have 1.6 grams of pyrolusite ore which was treated with 50 ml 1 normal oxalic acid and some sulfuric acid. The volume of the oxalic acid left undecomposed was made up to 250 ml. 25 ml of this solution when treated with 0.1 normal KMnO4 solution required 32 ml of it. Then you have been asked to find the weight percentage of pure MnO2. Right, now you can see here that the pyrolusite ore is an ore of the manganese. The compound is MnO2. Now we have taken 1.6 gram of such MnO2 which was added some oxalic acid. I mean to say 1 normal of oxalic acid in presence of H2SO4. Sulfuric acid is acting only as the acidic medium here, and you had been given the volume of oxalic acid as well, that is 50 ml. Now this solution, the volume of oxalic acid left undecomposed. I mean to say that in acidic medium, no matter what is the oxidation state of manganese, would change to +2, and here oxalic acid, where the oxidation state of carbon is +3, would be changing to +4. I mean, this is oxidizing agent reacting with a reductant or reducing agent here, leading to the formation of carbon dioxide and Mn+2. Now, after knowing this, we should see here that there is some oxalic acid is left undecomposed. That means we have taken here the excess amount of the oxalic acid. We have taken excess, that is the reason why some oxalic acid is remaining. I mean to say here this MnO2 substance is reacting or acting as the limiting reagent. Now it is given to find the excess of oxalic acid that is remaining in the solution. You have back titrated. Remember my dear students, when the substance which is added in the first reaction remains, when you try to find out its amount by doing titration once again, you call it as back titration, and you could see here that this was made up to 250 ml and 25 ml of this remaining oxalic acid was back titrated with 0.1 normal 32 milliliter of KMnO4. Once again here manganese, anyways the acidic conditions are there, manganese will change its oxidation state to +2, and here the product formed from the carbon is +4, that is nothing but carbon dioxide. So what I mean to say here, when we say that the equivalence or gram equivalence of KMnO4, which is equal to normality into volume in liter, which have reacted with the oxalic acid remaining, I can write here this could be equal to the oxalic acid remaining, but these equivalents are present in 25 ml. So here when you find out the equivalents of KMnO4 are nothing but the equivalents of oxalic acid, but in 25 ml the original solution is in 250 ml. So in order to find out the equivalents of this oxalic acid which are initially present in 250 ml, you have to equate that with the KMnO4. Along with that you have to multiply this with 10 so that you can get this multiplication factor. You can see that these are the equivalents which are present in 25 ml, hence I am finding out the equivalents in 250 ml just by multiplying with 10. Now these are the equivalents of oxalic acid that are remaining after the first reaction, and you had been given the equivalents of oxalic acid which are being initially taken as 1 into 50 into 10 to the power minus 3, that is normality into volume in liter. Volume is given in milliliter, I am dividing with 1000. So here you can see my dear students that this is 32 into 10 power minus 3. These are the equivalents of sulfuric acid remaining. These are the equivalents of oxalic acid remaining. These are the equivalents of oxalic acid which are initially taken. Therefore, the oxalic acid equivalents that have reacted with pyrolusite are nothing but the equivalents of pyrolusite. As per the law of chemical equivalence, whenever two substances react, their gram equivalents are equal. So initially this many equivalents are present, these are the equivalents that are remaining. So the difference in equivalents of oxalic acid has reacted with MnO2, hence equal to the equivalents of MnO2 is nothing but 50 minus 32, that is 18 into 10 to the power minus 3. So when I write gram equivalents, I will mention it as weight upon equivalent weight, that is gram molecular weight divided by n factor of MnO2, which is changing from +4 to +2. So from here you will be finding out the weight of MnO2 in the sample. You can see there is only one unknown, that is nothing but the weight of MnO2. Therefore, you have been asked to find out the percentage of MnO2 in the pyrolusite sample, which is equal to weight of MnO2 divided by the total weight of the sample is 1.6 gram multiplied by 100. Now, when you simplify this by substituting the weight of MnO2, you will be getting it as approximately 49% by weight of MnO2 present. In the next question, equal weights of mercury and iodine are allowed to react completely to form a mixture of mercurous and mercuric iodide. Then you have to find out the weight ratio of the mercurous and mercuric iodide that are formed during this reaction. So, in this case, you have been given the mercury and iodine reacting in equal weights. You know that initially you will be getting mercurous iodide, which will subsequently react with iodine present in excess or remaining in the first reaction to give you mercuric iodide. As we are aware of the fact that mercury changing its oxidation state initially to +1, from there it is changing to +2 because these are the oxidizing agents. Halogens are the oxidizing agent which are oxidizing initially the mercury from 0 to +1 and then from +1 to +2. Some students get confused here how to write the products. Here the logic is very simple. It's a simple redox reaction and we will acquire initially the lower oxidation state and we will be reaching the upper then. Now you had been given the information that you have taken the equal weights of these two. Suppose I have taken x grams of mercury and x grams of iodine. And now since we are going to use the mole concept, I am going to balance this equation first. You can see there are 2 mercury over that side, you have to multiply by factor 2, whereas here the total mercury that is involved on the product side is only 1, hence it has to be multiplied by 2, and now you can see that the total number of iodines that are involved in this reaction are balanced in either cases. So here after balancing the equation, I will convert the weight into the moles by dividing with the atomic or molecular weights respectively. You know that the atomic weight of mercury is 201 approximately and that of I is 127, and writing the molecular weight 127 into 2. Now these are the what you call number of moles of these two substances that are involved. Now we can see iodine is subsequently reacting in the second reaction, hence we can assume that this is acting as a limiting reagent. That means this is excess reagent that is remaining, that is the reason why it is reacting. Otherwise you have the standard methods to determine which one is the limiting reagent, right? Now here I am assuming this as the limiting reagent, and for every 2 moles of mercury I am getting only 1 mole of this mercurous iodide, hence for every x by 201 I can expect the formation of half of it, that is x by 402 gram moles of mercurous iodide is formed in this reaction. Now let us check out how much of I2 has reacted. For every 2 moles, once again 1 mole of I2 only has reacted. For every x by 201, as you all know, x by 402 gram moles of I2 will react, and the gram moles of I2 that are remaining are initial moles which are x by 254 which are taken, and the x by 402 moles of this I2 has reacted from this mole ratio 2:1 for every x by 201, x by 402. Now these amounts are ready. Now you can see, my dear students, these amounts are ready to react. I mean to say x by 254 and minus x by 402 amount of iodine and x by 402 amount of mercurous iodide are ready to react subsequently in the second reaction. Now we have to once again check which one is the limiting reagent, as here I can see clearly that this consumed is lesser than this, hence I am assuming this as the limiting reagent. For every 1 mole I am getting 2 moles of mercuric iodide. For every this much I will be getting the double of it, that is this much. For every 1 mole of mercurous iodide has reacted. For every x by 254 minus x by 402, I will be reacting the same amount of mercurous iodide. So when I subtract the initial and reacted, I will be getting the remaining moles of the mercury. I mean to say the number of moles of mercurous iodide that are finally remaining are this much after the second reaction, and the number of moles of mercuric iodide that are finally formed are this many after the second reaction. Now we all know that number of moles is equal to weight by molecular weight. Now therefore the weight ratio of mercurous iodide and mercuric iodide in terms of X can be obtained now by simplifying this expression we can get the value of this ratio. I mean to say, by simplification of this we will be getting this ratio as 0.513:1 or approximately 2:1. We have 1000 ml of oxygen at NTP which were passed through an ozonizer and the resulting volume is 888 ml. This quantity of ozonized oxygen was then passed through excess of potassium iodide. Then you have been asked to find the weight of iodine that is liberated. So here there are two concepts that are involved. One is related to the simple eudiometry, that means the analysis of the gas. The second one is the iodometry. I mean there is conversion of oxygen to ozone which is involved in the first reaction, but you can see here clearly that the entire conversion of oxygen to ozone is not possible since ozone is not stable at room temperature. Hence I am taking the equilibrium situation arising here. I have taken here 1000 ml of oxygen initially. When this is sent through the ozonizer, I will assume some X moles of oxygen has reacted or X milliliter of oxygen has reacted in this reaction at STP, and you can see here for every 3 moles there are 2 moles of ozone that are produced. For every 1 mole there are 2/3 moles. For every X it will be 2x/3 ml of ozone formed in this reaction. You can see once again we are using the gravimetry concepts. For every X ml, 3:2 is the mole ratio or 1:2/3 is the mole ratio. For every X ml that has reacted from oxygen, you can expect the formation of 2x/3. This I could make out because in the question it is clearly mentioned that this gas mixture, I mean to say oxygen and ozone, both should remain after the end of this reaction. I mean it's also given that the sum of the volume of these two gases is 888 ml. From here I will be finding out the value of X. It's 336 milliliter after the simplification. Now we know that out of these two, this is a better oxidizing agent. Now when this gas mixture is passed through Ki, there is only one chance that your ozone is going to react with Ki as per this reaction to give you iodine. Ozone is a better oxidizing agent because of the presence of nascent oxygen, and that is responsible for the oxidation of this potassium iodide into I2. And when you balance this equation, you will be getting for every 1 mole of this ozone, 1 mole of I2 is liberated. When you simplify this equation, you will be getting such an expression where you will be getting 2 moles of KOH, and I guess this equation is now balanced as well. Now you have been asked to find the weight of iodine which can be obtained through the number of moles of ozone. Now you see that number of moles of ozone which can be calculated as Tp as volume of ozone divided by 22,400 milliliter. Now you can see from here over there volume of ozone is 2x/3, that is 2 into we got the value of X. Now this upon simplification giving rise to 224 ml, that is 224 divided by 22,400, that is 1/100 mole of oxygen has reacted in this reaction. And for every 1 mole you are getting 1 mole of iodine, hence I will be expecting the formation of the same number of moles in case of I2 also, which can be written as weight upon the molecular weight. Now when you simplify this, you will be getting the weight of I2 obtained is 2.54 gram. So answer for this question is 2.54 gram, that is option A. Now we have 10 gram of a mixture of anhydrous nitrates of two metals A and B, which are heated to constant weight and gave 5.531 gram of a mixture of the corresponding oxides. The equivalent weights of A and B respectively are 103.6 and 31.8. Then you have been asked to find out the weight percentage of A in the mixture but not ANO3. I mean to say the nitrate of the mixture. What I mean to say that you have the nitrate of A as well as the nitrate of B. Here I am assuming that the valency of this A as X and that of B is Y. Then I am writing the entire compound as ANO3 taken X and BNO3 taken Y. Now this compound, when subjected to heating, is giving rise to the oxide. We don't know about the other components that are produced during this reaction, but we are sure of the fact that the oxides are obtained, and you have been given information regarding these two, that this mixture is weighing 10 grams and the oxides are weighing 5.531 gram. Now when you are given a mixture and the mixture has certain weight, now first we have to convert this in terms of X, then the weight of this will be 10 minus X gram. Now we know that the gram equivalents of ANO3 taken X, whenever we find the gram equivalents, when the weight is given, we divide the weight with the gram equivalent weight. I mean, you have the gram equivalents of ANO3 taken X as, or I'll assume this time it has A gram, and this will be 10 minus A, because already we have assumed here it has X. Now let's take it as A gram. Now the gram equivalents of this ANO3 taken X is weight divided by equivalent weight of ANO3 taken X, that is equivalent weight of A, which is provided to us 103.6, plus equivalent weight of nitrate ion, that is the molecular weight or formula weight divided by its valency, 62 divided by NO3 minus, hence I am writing 1 as the n factor here. Now these are the gram equivalents of ANO3 taken X, which are entirely changing into the A2OX, hence their gram equivalents are equal. And you are also given the gram equivalents of BNO3 taken Y, weight upon the equivalent weight of B is given as 31.8 plus equivalent weight of nitrate ion is this much, which are nothing but the equivalents of B2OY, because you know that the gram equivalents of two substances reacting with each other or formed from each other should be equal. Now when I write this as weight of A2OX, or I am going to write this as weight of A2OX divided by equivalent weight of A2OX, that is equivalent weight of A, once again 103.6, plus equivalent weight of oxygen, that is gram atomic weight by its valency, and the gram equivalents of this thing as weight of B2OY divided by the gram equivalent weight of this plus the gram equivalent weight of oxygen. Now it's known that the sum of weight of OX plus weight of B2OY is given as 5.531 gram. Now when I multiply and simplify this, I will be getting this over there. I can simplify this, 103.6 plus 8 divided by 103.6 plus 62 times of A. This is the weight of A2OX plus the weight of B2OY. You can see 31.8 plus 8 upon 31.8 plus 62 into 10 minus A. This whole weight is given to us as 531 gram. Now from this expression we will find the value of A. After finding the value of A, the only unknown of this expression, you can see there is only one unknown, that is nothing but A. After finding out the value of A, you can see here that we will be using that to find the percentage of A in the mixture, because you know that A is present only in the first compound, and you know that the gram equivalents of ANO3 taken X is equal to gram equivalents of A. Hence I will be writing the gram equivalents, that is weight of it by equivalent weight of it. These are the gram equivalents of this compound and nothing but the gram equivalents of this substance, which is equal to weight of A divided by equivalent weight of A. Hence weight of A is this many grams you got. You are substituting anyway the value of A here, then you have been given the weight percentage of A in the mixture as weight of A upon the total weight of the mixture into 100, that is 103.6 A by 165.6 into 10 is going to be your final answer. So here you will be substituting the value of A to get your right answer, and it is 32.28% of A is found in the mixture. We have a solution of hydrogen peroxide which is labeled as 20 volume, which was left open for some time. Due to this, some H2O2 decomposed and the volume strength of the solution is decreased. To determine the new volume strength of H2O2 solution, 10 ml of this solution was taken and it was diluted to 100 ml, and this diluted solution then picked up 10 ml, and this was finally titrated with KMnO4 using 0.025 molar and 25 ml of the solution. Then you have been asked to find the volume strength of H2O2. Now initially you have the sample of H2O2 which is written as 20 volumes, which was left open for some time. Then we got a new sample or decomposed sample of H2O2. Its volume strength obviously will decrease because of the decomposition of H2O2, because you know that H2O2 is decomposing at room temperature itself to give you, it's a disproportionation reaction. You can see the change in oxidation state from -1 to -2, that is the reduction as well as the oxidation. Now this decomposed, we have taken 10 ml, this was added water, then we made it to 100 ml, then this was picked 10 ml. This solution, diluted H2O2, was titrated with KMnO4, which is given to us as 0.025 molar, 25 milliliter of it. Now, assuming that this reaction is taking place under acidic medium and the change in oxidation state, anyways, from +7 to +2, this is reduced, hence O2 will be oxidized, and subsequently finding out the N factor of this KMnO4 over here, as +7 to +2 is the change, then the N factor is 5. Now you will be writing the gram equivalents of KMnO4 in acidic medium have reacted with the H2O2 in 10 ml diluted solution. Now the gram equivalents of any two substances reacting are equal. The gram equivalents of KMnO4 as per this data is molarity. When we multiply the molarity with the N factor, we will be getting the normality to 25 divided by 1000. That is normality, molarity into N factor into volume in liter. Volume in liter, we got the equivalents of KMnO4 which has reacted with the equivalents of H2O2 in dilute phase. Now we know that when the gram equivalents of H2O2 over here are this many, the gram equivalents of this H2O2 in 100 ml will be 10 times of it. I mean to say 0.0245 into 125. I am simplifying this, divided by 100. I am multiplying this with 10 so that I can get the gram equivalents of this thing in 100 ml, because I know that these are in 10 ml. Hence, to find out in 100 ml, I am multiplying this with 10, where the 0 got cancelled and we got this information. Now we know that these are the gram equivalents of H2O2 which are present in 10 ml of original solution. I mean to say this solution have the equivalents equal. Suppose if I assume that the equivalents of H2O2 over here are E, here it will be E as well, because upon dilution the gram equivalents does not change. Whereas when you pick some amount from it, it will become 1/10 of it, because you have picked up 10 ml of dilute solution from that. I am repeating here, the gram equivalents does not change, or gram moles weight does not change upon dilution. Here if the gram equivalents are E, here also it will be E, but when you are picking up certain amount from it, it will be reduced. I mean to say here 100 ml has become 10 ml, then accordingly the gram equivalents of H2O2 will be decreased. And now these are the gram equivalents of H2O2 that are present in 10 ml original solution. This is dilute, this is original solution. Now after getting the gram equivalents of H2O2 in original solution, you will be finding out the normality of H2O2 equal to gram equivalents of H2O2 divided by volume of the solution in liter. When you divide the gram equivalents with the volume, you will be getting the normality, and you know finally that the volume strength of H2O2 solution is 5.6 times of normality of H2O2. Hence when I multiply that entire value with 5.6, I am going to get my answer. I mean to say the volume strength of H2O2 finally is obtained as 17.136 volumes. You can see here it has decreased, and the answer for this question is 17.136 volumes. We have 200 milliliter of a solution of a mixture of sodium hydroxide and sodium carbonate, which was first titrated with HCl using phenolphthalein as indicator, and HCl required was 17.5 ml for this endpoint. After this, some methyl orange was added, and 2.5 ml of the same HCl was again required. I mean to say the stock solution was required for the next endpoint. I mean to say for the methyl orange endpoint, and you have to find out the amounts of NaOH and Na2CO3 in the mixture. Now you know that when you are adding, since you have taken a mixture of sodium hydroxide and sodium carbonate, as far as the basic strength is concerned, sodium hydroxide is a stronger base. Now when you are adding HCl in it, the first reaction will be between these two, where you will not be able to find or trace out any end point, because the conjugate base of phenolphthalein, because you know that this you have added along with the phenolphthalein, which is going to react with it. Phenolphthalein is a weak organic acid. It has reacted, a pinch of it you have added, it has reacted with the base mixture to get converted into this, which is pink in color. I mean to say you have the entire solution now in pink. It is desperately waiting for the proton to come, but NaOH has not given it the opportunity to take the proton because it's a stronger base. Now when you are adding HCl again, sodium carbonate is going to pick that because it is second best base, and as soon as this gets converted into sodium bicarbonate along with NaCl, this PHE minus, I mean to say the phenolphthalein conjugate base, is going to pick the proton from it and quickly going to get converted into the colorless form of phenolphthalein, and this lies the end point of phenolphthalein titration. So at this point you can see that whatever equivalents, gram equivalents of HCl that I have added have reacted with sodium hydroxide as well as sodium carbonate partially. Hence I will be writing the gram equivalents as, because I have to find out the weight of each, weight upon the n factor. I mean to say the gram equivalent weight, that is molecular weight upon n factor. You can see here number of replaceable OH minus 1 have to be accounted for. It is 1 plus the gram equivalents of Na2CO3, weight of Na2CO3 divided by equivalent weight, that is molecular weight divided by, here you have to guess the n factor of HCl, which is nothing but 1. Don't take it as 2 because the total charge is 2. Here only one HCl has, only one H plus has been taken by sodium carbonate. We have to take the n factor of this sodium carbonate as 1. If 2 H plus are taken by this base, then we will take the n factor as 2. But only partial neutralization is taking place. We have to take the n factor as 1, which is equal to the normality of HCl, which is given as 1 normal, and the volume of HCl which is used for the titration is 7.5 milliliter. So when I multiply the normality with volume in liter, I will be getting the gram equivalents. Now these are the gram equivalents of HCl which have reacted for the phenolphthalein end point. Now what we did is we have added some methyl orange and we continued our titration. We know that sodium carbonate is the only substance which is left over to react with the HCl, and when you add this methyl orange over there, it will quickly grab H2CO3, yellow in color, and after grabbing this it will be converting it to conjugate base, conjugate acid, which is red in color. I am going to say H2CO3 is essential for the conversion or change of color of methyl orange. So when this takes place, I am going to say this reaction takes place or the formation of H2CO3 takes place, we say that as the methyl orange end point, and we note down the volume of HCl which has been added. It is given in the problem as 2.5 milliliter. Now we know that the gram equivalents of HCl that we have used, which is equal to the same stock solution which has been used exclusively only for sodium bicarbonate reaction. And you can see initially we didn't take any sodium bicarbonate in our mixture. So we have to see from where we have obtained the sodium bicarbonate. So you can see clearly that sodium bicarbonate is obtained from sodium carbonate, hence their gram equivalents are equal. Once again I will be writing this as weight upon equivalent weight, that is molecular weight upon n factor. So now we have one more expression for the weight of Na2CO3. So we have two equations. One is pertaining to the weight of NaOH as well as Na2CO3. The second one is we have only the weight of Na2CO3 as the unknown. Now simplification of these two equations or solving these two equations will fetch you the value of NaOH as well as, I mean to say, the weight of NaOH as well as Na2CO3, which are obtained as 0.06 gram and 0.027 gram of these two. The next question is again on double titration. We have 50 ml of a solution containing 1 gram each sodium hydroxide, sodium bicarbonate and sodium carbonate, and were titrated with 1 normal of HCl. You have been asked to find the titer readings, I mean to say the volume of HCl in each case. In the first case, we have used only phenolphthalein as the indicator. In the second one, we have used only methyl orange as the indicator. In the third one, we have taken methyl orange as well as, I mean to say, phenolphthalein. But methyl orange was added after the phenolphthalein end point. So when you see here, in the first case, when you have added only phenolphthalein as the indicator, you know only two bases that are present as I just discussed. One is NaOH, the second one is sodium carbonate, and you know only partly it will react, because what we require is a replaceable hydrogen atom for the conjugate base of the phenolphthalein. Hence you will be writing this expression. These two have reacted with HCl. So weight of NaOH is mentioned to us in the problem as 1 by equivalent weight, that is molecular weight by n factor. Weight of Na2CO3 is also the same. N factor once again here is only 1 because it has taken only one hydrogen to undergo partial reaction, is equal to normality of HCl into volume in liters. So this is your first titer reading when you use only phenolphthalein. The second question is when you have used methyl orange after phenolphthalein end point. So after phenolphthalein, you know that your solution has only NaHCO3, which is taken initially, because initially also you have taken sodium bicarbonate, and NaHCO3 is produced by the reaction of its sodium carbonate with HCl, and the total NaHCO3 is reacting with HCl to give you H2CO3. So as I just told you, we require H2CO3 to change the color of methyl orange from yellow to red. Now we will stop our titration and we will say that the gram equivalence of HCl has entirely contributed to the sodium bicarbonate total. I mean to say the gram equivalence of sodium bicarbonate which we have from the beginning plus the gram equivalence of NaHCO3 obtained from Na2CO3 and nothing but the gram equivalence of Na2CO3 itself. So when you write this expression, weight by equivalent weight plus weight by equivalent weight, turning out to be the normality into volume for this thing. I mean to say this time I have taken, say it as V1 ml. Now simplification will fetch you the values of V1 and V2. Now in the third case, only methyl orange is being used. So from the beginning we have used only methyl orange. That means you have added HCl, NaOH will completely react. No change in the color of methyl orange, it requires only H2CO3. Next your Na2CO3 completely reacts, it doesn't require partial reaction because there is no phenolphthalein. You will be getting H2CO3, and also your sodium bicarbonate can contribute to give you H2CO3. I mean to say your HCl whichever you have taken here for the methyl orange only has reacted with all the three. Weight upon equivalent weight in every case. This time I will assume that the volume of HCl required is V3. The simplification of these three equations will fetch you the values of V1, V2 and V3. V1 you will get as 34.4 ml. V2 will be 55.8 and V3 is 20.8 ml. In the next question we have a definite amount of barium chloride and HCl with unknown normality. 20 ml of this solution was treated with 21.4 ml of 0.1 normal NaOH for complete neutralization. Further, 20 ml of the same was added 50 ml of sodium carbonate 0.1 normal, and the precipitate was filtered off, and the filtrate reacted with 10.5 ml of 0.08 normal H2SO4 using phenolphthalein as indicator. Calculate the strength of barium chloride and HCl in the mixture. That is, you have been asked to find the weight of each in the mixture. So in this case, we have a mixture of BaCl2 and HCl. Now this mixture was first treated with NaOH, where we all know that only HCl is going to react with NaOH. So here, when I treat this and equate that to the equivalence of HCl, that is equal to equivalence of NaOH, normality is given as 0.1 and volume is 21.4 in milliliter, hence I am dividing with 1000 so that I can get the volume in liters. These are the equivalents of HCl, weight upon equivalent weight. So weight of HCl in 20 ml is this many grams. Now if these are the equivalent that are present in 20 ml, you can find out the weight of HCl in 1 liter by multiplying with 1000 by 20, that is 50. Now this many gram per liter are present in the given solution, and the weight of HCl in this case is obtained as 3.9 gram. So this is one question which we need to solve. Now this is one pertaining reaction. Now after knowing this, you know that you have once again taken 20 ml of this solution, which was added Na2CO3. Now this time what you did is you have treated this with Na2CO3, hence I can anticipate this Na2CO3 to react with BaCl2 as well as HCl, and BaCl2 was completely eliminated, and whichever Na2CO3 is remaining had been titrated by using 0.08 normal 10.5 ml of H2SO4. That is, here when you have added this barium chloride and HCl with Na2CO3, you have added in excess. Both the substances have reacted. Your barium carbonate precipitated is eliminated. The precipitate is taken off, and the filtrate, whichever we have, the excess or remaining Na2CO3 was back titrated with H2SO4 using phenolphthalein as the indicator, and the information provided to you is regarding the H2SO4 0.08 normal and 10.5 milliliter. Hence you will be writing the gram equivalence of H2SO4 is equal to normality into volume in liter. So these are the gram equivalents of H2SO4 that has reacted with Na2CO3, and nothing but the equivalents of Na2CO3 that are remaining in the solution. Now we know that the Na2CO3 which has been initially added in excess over here, information is provided to you, 0.1 normal and 50 milliliter of it. Now you see the equivalence of Na2CO3 which have reacted with the mixture of the two is the difference. Now this difference will give you the equivalence of Na2CO3 which has reacted with barium chloride as well as HCl, and as I told you, when substances react, their gram equivalents need to be taken as same. What I mean to say, that the gram equivalents of barium chloride plus, I am going to substitute the equivalents of HCl that are present out there, and nothing but 0.1 into 21.4 upon 1000 is equal to this much. So therefore I will write this as weight upon equivalent weight, 137 plus 71 is the molecular weight upon the N factor of barium chloride in this reaction is the total charge, is taken as that much, this giving rise to the weight of BaCl2 present in 20 ml. Now after getting weight of BaCl2 present over there, when I multiply this with 50, I'll be getting the weight of BaCl2 that is present in 1 liter of the solution, and the answer for this is 6.1 gram. We have a mixture of calcium carbonate and sodium chloride weighing 3.2 gram was added 100 ml of 1.02 normal of HCl. After the reaction had ceased, the liquid was filtered and the residue was washed and the filtrate was made up to 200 ml. 20 ml of this solution then required 25 ml of 0.2 normal NaOH for complete neutralization. Then you have been asked to find the weight percentage of CaCO3 in the mixture. Look at here that you have a mixture of the calcium carbonate as well as NaCl. This was added HCl, and certain data is provided regarding the HCl. That is, we have taken 1.02 normal and 0.1 liter of HCl had been taken. As you all know that this is an alkali, is going to react with the HCl, hence you will be writing the expression the gram equivalents of acid and base are equal. So now after writing this, I can see that these are not the equivalents of HCl which have completely reacted with the calcium carbonate, because the information clearly provided to you is that you have taken the excess of HCl, because the residual solution which was initially made up to 200 ml was then back titrated. I mean to say that 20 ml of this solution was back titrated, residual HCl was back titrated with NaOH requiring n by 5 and 20 ml. What I mean to say that the equivalents of NaOH which you have used have been used for the remaining HCl in 20 ml. Hence, to find in 200 ml, I have to multiply this with 10. Now, these are the equivalents of HCl that are remaining over here. That means these are the equivalents which you have taken initially, and these are the equivalents of HCl that have remained during the reaction. When you subtract these two, you will be getting the gram equivalents of HCl which have exactly reacted with the calcium carbonate. So here you can see, my dear students, this is again the question on back titration, where you had been given how much of NaOH you require to exactly find out how much of HCl is remaining after the first reaction, because you have taken excess of this. After adding HCl, you know that CaCO3 despite completely reacted, some HCl remaining, and that HCl was found out by using the NaOH and its equivalent. So the gram equivalents I found, normality into volume in liter. These are the present in 20 ml, hence I found out in 200 ml by multiplying with 10. Then we have the equivalents of HCl that are remaining. This many equivalent HCl we have added initially. This many are remaining. Then the reacted are the difference, which I will be writing as weight upon equivalent weight. That is molecular weight upon n factor is turning out to be this much. So from here I will be finding out the weight of CaCO3, and the weight percentage of CaCO3 is weight of CaCO3 upon the initial weight of the mixture is given to you as 3.2 gram, and the answer for this question is 81.25% approximately. We have 2 gram sample of a mixture containing sodium carbonate, sodium bicarbonate and sodium sulfate, which is gently heated till the evolution of CO2 is ceased. The volume of CO2 at 750 millimeter of mercury pressure and 298 Kelvin is measured to be 123.9 ml. And 1.5 gram of this same sample required 150 milliliter of 0.1 molar HCl for the complete neutralization. Then you have to find out the percentage composition of each component in the mixture. Here you have to understand that you have taken a mixture of sodium carbonate, sodium sulfate and sodium bicarbonate. So here when you have taken the three and when you have heated it gently, the carbon dioxide evolved is mainly from sodium bicarbonate. As we all know that this is not going to dissociate. The carbonates of 1A are stable, whereas the bicarbonates are unstable. Hence, carbonate do not undergo any decomposition, but bicarbonates undergo. So when I simplify this, I am going to get this. Now in this, the total weight of the sample is 2 gram. Here if I assume this as x gram, this is y gram, then this will be 2 minus of x plus y gram. And when I divide this with the molecular weight of the substance, I will be getting the gram moles. Because this is a simple gravimetric question, I can use mole concept because I can easily balance this expression. For every 2 moles, there is 1 mole of sodium carbonate which is being produced and 1 mole of CO2. Since you have been given information regarding the moles of CO2, it is better to convert the moles of NaHCO3 into the moles of CO2. Now for every 2 moles, I am getting 1 mole of carbon dioxide. For every this much, I can expect the formation of half of it. These are the number of moles of CO2 which are formed, half of this entire value. Now, which is equal to, these are nothing but the number of moles of carbon dioxide, which is equal to, I am using the ideal gas equation here because I have been provided with pressure, volume and temperature. Pressure is 750 by 760 in atmosphere, into volume is 123.9, that is 0.124 liter divided by RT. The temperature over there is mentioned as 298. Now these are the number of moles of CO2. That means you have got one equation in terms of x and y. One equation, 2 unknowns are not sufficient. Then you have to see that 1.5 gram of the same sample required 150 ml of the HCl for complete neutralization. Now when you are using HCl, we all know that sodium bicarbonate as well as sodium carbonate are going to react completely with HCl. These are the concerned reactions. So what I mean to say that the gram equivalence of HCl which you have used totally, that is 0.1 normality into volume in liter, are going to be used for Na2CO3 as well as NaHCO3. So I am writing this as weight of Na2CO3, that is weight of Na2CO3. This Na2CO3 weight you have taken in x gram. X is per 2. For 2 grams of the sample, you have taken x grams of Na2CO3. Here 1.5 gram of the sample was being taken, and if it is for 2 gram, if it is x, 1.5, it will be 1.5 into x divided by 2. This is the weight of Na2CO3 which is present in 1.5 grams divided by equivalent weight of Na2CO3, that is molecular weight, divided by, this time the n factor is 2 because the complete neutralization is taking place, plus the weight of sodium bicarbonate. You can see here that it is 1.5 by 2 times of 2 minus of x plus y divided by 84 by 1 because it has taken only one HCl is equal to 0.015. Now you got one more equation in terms of x and y. You got 2 equations and 2 unknowns to be obtained. They are x and y, and after that you will be finding out the weight percentage of NaHCO3 as somewhere around 42%, and the percentage of Na2CO3 somewhere around 26.5%. So this is the answer for your question in stoichiometry.